day everyone, welcome again in our laboratory. From the previous video, we talked about mass spectroscopy and its subtopics. But now we will move on to analytical separations. But before proceeding, let me present to you our learning objectives and our conceptual framework. Now, let's proceed with the discussion.
Good morning everyone. In this video, we will be learning about what is analytical separation. So when we talk about analytical separation, it's either we can talk about solvent extraction or chromatography. So we will talk first the solvent or the idea of the solvent extraction. So is to take advantage of differences in solubility of analyte in different solvent. Next is you can also manipulate pH to improve extraction efficiency. And next is you can use metal chelators to extract metals. In chromatography, it is more an active technique. It means that you're passing your analyte through a stationary phase or mobile phase. And you're gonna get separation by differences in partitioning whether your analyte has been in mobile phase or stationary phase. In this case, you can use temperature, dissolvent polarity, stationary phase polarity to improve your separation. In solvent extraction, it requires two immiscible phases. It's either the phase 1 or the phase 2. The idea is that your analyte has different solubility in phase 1 or phase 2, or you need to establish an equilibrium of the analyte in different phases. And it is represented by what we so call the partition coefficient of solute between the phases. The goal of the analytical separation is to remove either the analyte or the interferent from the sample matrix. To achieve this separation, we must identify at least one significant difference between the analytes and the interferent's chemical or physical properties. A significant difference in properties, however, is not sufficient to effect a separation if the conditions that favor the extraction of interferent from the sample also removes a small amount of the analyte. There are two factors limits a separation efficiency. First is to failing to recover all the analyte, and the second one is to failing to remove all the interferent. So let's proceed to the significance of analytical separation. So analytical separations are from only being a mature routine techniques with limited potential for innovation. These techniques are established tools in industry and academia owing to their high separation power and excellent performance or the cost ratio. However, they are also one of the most important driving forces for innovation in many established and emerging areas of science. The application for analytical separation is processes are often classified according to the particular differences they use to achieve separations. If no single difference can be used to accomplish the desired separation, multiple operations can often be combined to achieve the desired end, with a few exceptions. Elements or compounds exist in nature in an impure state. Often these raw materials must go through a separation before they can be put to productive use, making separation techniques essential for the modern industrial economy. Also, the purpose of separation may be analytical, can be used as a like component in the original mixture without any attempt to save the fractions, or may be preparative or to prepare fractions or samples of the components that can be saved. The separation can be done on a small scale or effectively a laboratory scale for analytical or preparative purposes, or on a large scale effectively an industrial scale for preparative purposes or on some intermediate scale. So we will be moving on to the principle of analytical separation. The separation of chemical components is performed using chromatographic technique. As we all know that chromatography is an analytical technique used for separating a mixture of chemical substances into its components so that these can be identified or analyzed.
So now let's discuss about the different types or different separation technique. So we all know that a separation process or technique is a method that converts a mixture or solution of chemical substances into two or more distinct products mixture. Processes and techniques are often classified according to the particular differences they use to achieve a separation. If no single difference can be used to accomplish a desired separation, multiple operations can often be combined to achieve the desired end. Now let's discuss the different types of separation technique. First is we have the filtration. This is more common method of separating an insoluble solid from liquid. An example of such mixture is sand and water. Filtration is used in water treatment plants where water from rivers is filtered to remove solid particles. Filtration is any various mechanical, physical, or biological operation that separates solid from fluid by adding medium through which only fluids can pass. The fluid that passes through is called the filtrate. Next is we have the simple distillation. Distillation is the process of separating the components or substances from a liquid mixture by selective boiling and condensation. This method is best for separating a liquid from a solution. In a way, the concept is similar to evaporation, but in this case, the vapor is collected by condensation. For example, if you want to separate water from a salt solution, simple distillation would be great for this. Next is we have the crystallization. It is the natural or artificial process by which a solid forms, where the atoms or molecules are highly organized into a structure known as a crystal. Some of the way which by crystals form are precipitating from a solution, freezing or rarely deposition directly from a gas. Attributes of the resulting crystal depend largely on factors such as temperature, air pressure, and in the case of liquid crystals, or time of fluid evaporation. Next technique is we have the recrystallization. It is a technique used to purify chemicals by dissolving both impurities and a compound in an appropriate solvent. Either the desired compound or impurities can be removed from the solution, leaving the other behind. Next is we have the sublimation. Sublimation is the transition of substance directly from the solid to the gas phase without passing through the intermediate liquid phase. Sublimation is a technique used by chemists to purify compounds, and a solid typically placed in sublimation apparatus heated under vacuum. Next technique is what we call centrifugation. It is a technique which involves the application of centrifugal force to separate particles from a solution according to their size, shape, density, viscosity of the medium, and rotor speed. This process is used to separate two miscible substances, but also to analyze the hydrodynamic properties of macromolecules. Lastly, we have extraction. Extraction in chemistry is a separation process consists in the separation of substance from a matrix. Common examples include liquid-liquid extraction and solid phase extraction. The distribution of a solute between two pieces is an equilibrium condition described by partition theory.
Let's proceed with the classifications of separation techniques. We can separate an analyte and an interference if there is a significant difference in at least one of their chemical or physical properties. On this table, we can see the list of separation techniques organized by the chemical or physical properties affecting the separation, which are size, mass or density, complex formation, change in physical state, change in chemical state, and partitioning between phases. Now let's start with separation based on size. Size is the simplest physical property we can exploit in a separation. To accomplish the separation, we use the porous medium through which only the analyte or the interferent can pass. Example of size-based separation include filtration, dialysis, and size exclusion. Next is the separation based on mass or density. If the analyte and the interference have different masses or densities, then a separation using centrifugation may be possible. The sample is placed in a centrifugate tube and spun at a high angular velocity measured in revolutions per minute or RPM. These samples constituents experience a centrifugal force that pulls them toward the bottom of the centrifuge tube. Those species that experience the greatest centrifugal force have the fastest sedimentation rate and are the first to reach the bottom of the centrifuge tube. If two species have the same density, their separation is based on a difference in mass, with the heavier species having the greater sedimentation rate. If the species are of equal mass, then the species with the larger density has the greatest sedimentation rate. Next is the separation based on complexion reaction or masking. One widely used technique for preventing an interference is to bind the interferent in a strong soluble complex that prevents it from interfering in the analyte's determination. This process is known as masking. A wide variety of ion and molecules are useful masking agents, and selectivity is usually not a problem. Next is the separation based on a change of state. Because of an analyte that its interferent are usually in the same phase, we can achieve a separation if one of them undergoes a change in its physical state or its chemical state. Now, changes in physical state. Distillation, sublimation, and recrystallization are used when the change in physical states affect the separation. When the analyte and the interferents are miscible liquids, separation by distillation is possible if their boiling points are significantly different. The progress of a distillation as a plot of temperature versus the composition of mixtures vapor phase and liquid phase. The initial liquid mixture or the point A contains more interferent than analyte. When this solution is brought to its boiling point, the vapor phase in equilibrium with the liquid phase is enriched in analyte, which is the point B. The horizontal line that connects point A and B represents this vaporization equilibrium considering the vapor phase at point B. By lowering the temperature creates a new liquid phase with a composition identical to that in the vapor phase, which is the point C. The vertical line that connects point B and C represents this condensation equilibrium. The liquid phase at point C has a lower boiling point than the original mixture and is in equilibrium with the vapor phase at point D. This process of repeated vaporization and condensation gradually separates the analyte and the interference. When the sample is a solid, sublimation may provide a useful separation of the analyte and the interferent. The sample is heated at temperature and pressure below the analyte's triple point, allowing it to vaporize without passing through a liquid state. Condensing the vapor recovers the purified analyte. A useful analytical example of sublimation is the isolation of amino acids from fossils, mollusks, shells, and deep-sea sediments. The last technique in physical state is the recrystallization, which is another method of purifying a solid. Now, in the change in chemical state, the technique for separating analyte in chemical state are precipitation, electrodeposition, and volatilization. The last classification is partitioning between phases. The technique for separating analyte are extraction and chromatography. We call the process of moving a species from one phase to another phase an extraction. Simple extractions are particularly useful for separations where only one component has a renewable partition coefficient. Several important separation techniques are based on a simple extraction, including liquid to liquid, liquid to solid, solid to liquid, and gas to gas extractions. Another is chromatography that provides both a separation of analyte and interference and a means of performing a qualitative and quantitative analysis for the analyte.